Welcome back, class. And so let's continue chapter 9 and do some numerical examples and problems based on the material we just covered related to the low frequency response of the CS and CE amplifiers. So I mentioned that there are two important things that we work on in terms of problems, and I think I only mentioned got to talking about one and skipped the other. So what are these two things? First of all, we need to find a value for the minus 3 dB frequency, right? We need to know at what frequency can we say we have achieved the low frequency limit, below which, generally speaking, we cannot rely on the amplifier to be working efficiently or delivering the result that we want. So that low limit, also shown as FL in this drawing, generally is tied to FP2, which comes about, like I said, either it's dependent on the capacitor we used to bypass either the source or the emitter in case of the BJT. So that one capacitor, if the other capacitors meet the conditions, then that one capacitor in the source circuit or bypassing the source circuit or bypassing the emitter circuit becomes quite important, because as we can see from the drawing, the minus 3 dB frequency FL is almost always determined by this FP2, which is the break frequency because of the bypass capacitor. Okay. So that is part A of what we need to do. Part B, of course, is to find the value of the capacitors, right? As we are designing a circuit, so far we never bothered about it. We just assume that certain capacitors will be available that act like short circuits in the frequency range that of interest. But now we have to say what values of those capacitors should you choose to meet certain conditions. So if you're designing an amplifier, even if you're designing an audio amplifier, we know audio amplifiers can go from 20 hertz to 20,000 hertz, right? That's the audible frequency, the frequency at which the human ear can catch. So the lower end is 20 hertz, the upper end is 20,000. Can you design an amplifier all the way to 20 hertz? You can, but what it will cost you is some money, some expense in capacitance value. That means you have to buy some extra capacitors. If you want to save some money, then you can say, okay, my lower frequency is not 20, I'm happy with just having 100 hertz and above, right? Because 20 to 100, really not too much sound comes in that region. If you have above 100, you're okay. Then the cost of your capacitance may be lower, because one rule is that the amount of capacitor value is inversely proportional to the frequency. So the lower you want to go, the more expensive, the higher the capacitor, which means the more money the more expense you'll see. So these are some basic rules, but using these rules and the formulas that we found for CC1, CC2 and the CS capacitor, the three capacitors, we can use those formulas to calculate the capacitance. So then the two issues are obviously related to each other. you want to know what low frequency you can get to as the cutoff frequency FL. Similarly, to get to that low frequency, what capacitance values should you will you be looking at? So these are the two items that we address, we discuss when we do problems. The problems are not too difficult, at least in this section. I call it section A, part A of this chapter. Part B, the high frequency, slightly more complicated, but overall I think the problems in this, in at least the material we are covering in frequency response, are not too difficult, but at the same time they expose you. I hope my lectures here, the 2 days of lectures, help you address the issues of frequency response. Firstly, we kind of revised what we already know about frequency response from previous courses. We also looked at filters, and how to write the transfer function, HW, H omega, the gain as a function of frequency. Then we know how to convert it into decibels. We know what the 0 dB point is generally. And then for real amplifiers, we know that the mid-band gain is not just 0 dB, it can be 20 or 30 or whatever, depending on the voltage or the current gain, which is then converted to decibel. Then we also discussed a little bit on the standard form of the high-pass filter and how, with the amplifiers we are seeing here and the 3 capacitors, each capacitor can be found to have one breakpoint, and how to track that breakpoint we saw by using this method, where, for example, for omega p3 or fp3, because of this coupling capacitor cc2, the breakpoint frequency can be derived as 1 by RC, but R and C are slightly a bit more C, of course, there's only one C. R generally is a product or sum of 2 or 3 different resistances. So that's all we did so far. Let's move on to example 9.1 from our textbook. So this is the first numerical we are doing. This relates to a CS amplifier, and as shown in the circuit drawing here, we have 3 capacitors and of course an NMOS device. So these 3 so let's read the problem. So this problem is related to finding the values of CC1, CC2 and CS given a goal of a certain breakpoint or 3 dB or minus 3 dB frequency. What is that minus 3 dB frequency? It's 100 Hertz. So on the low end of the frequency ability of our amplifier, the signal frequency, the lowest we care about is 100 Hertz. So anything below 100 Hertz, even if there is not good amplification or all kinds of distortion comes in, the waveform is not clean AC in isn't clean AC out, we don't care. But above 100 Hertz, we want it to be clean. Okay. So the lowest frequency, the limit of our amplifier response on the low side is 100 Hertz. So to get 100 Hertz and all the other data about the resistances is given, GM is given. So with all this information, find CC1, CC2 and CS. Now we know CS is the most important thing because that directly generally ties to FL. But you can't ignore CC1 and CC2 also. They have to follow certain rules. So the break frequencies created by these two, they have to be much lower than the break frequency created by CS. If you satisfy that condition, then you have met all the rules that we just learned about. Okay. All right. So with all that, here are the three important relationships that you have to use. For the first break frequency due to CC1, this is the formula. I just copied it from the material we just covered. Obviously, this CC1 relies on the resistances close to it, which is our signal and our G, the gate bias resistance. The W omega P3, which is this, relies on the load resistance and the drain resistance. Lastly, this C, the bypass across the bias, the current source, that relies on the internal resistance of the device, which is represented by GM, right? GM is 1. So 1 by GM is your resistance, right? Because GM is a opposite of resistance, it's a conductance. So 1 by 1 milliamp is about 1000 ohms. So there is 1000 ohm resistance inside this device that affects the omega P2, and hence it helps us decide. Now this omega P2 is close to this 100 Hertz, so that helps us decide the value of CS. Generally you will find that this capacitance is very high compared to these other two. So the most costliest capacitance here, if you think, cost of capacitance directly proportional to the value of the capacitance, that's the cost of a capacitor. So this is an expensive capacitor because it is higher value. Okay. So you can see it's a pretty simple, problem. I shouldn't waste too much time. But if you can plug in all the answers or the data given to us, you will find that CS is about 1.75 microfarads, CC1 is 3.3 nanofarads, and CC2 is 0.53 microfarad. So the highest capacitance is CS, and yeah, with the rules, and if you need 100 Hertz, right? So the 100 is decided mostly by, like I said, CS, but the rule is also that the other two have to be much lower. That means the frequency breakpoint here, P1 and P3, which are shown here, FP1 and FP3, they have to be much lower. And here he says a factor of 4, but in our problem, in the textbook, example 9.1, if this is 100, he takes this to be 10, around 10. So if these are about 10, then between 10 and 100, there's enough distance, right? It's 10 times. The rule here is at least 4 times. So if you pick, 20 also, you're okay because 20 times 4, 100 is greater than that. So, but in our textbook, he picked 10 Hertz, and using that 10 Hertz on the left side here, well, 10 Hertz converted to radians, you can set this equation up and find CC1, CC2. Similarly, for this, you use 100 and find CS. Okay. So that was the first example, and I hope it's easy enough that you're confident that you know now enough about some frequency response uh, material theory as you start getting more and more deeper into studying amplifiers, FET amplifiers, BJT amplifiers, discrete amplifiers, IC amplifiers. You'll probably study a lot of those, but always remember frequency response is an important topic to go with it. All right, let's see what the next problems are. Okay, so I've come to example 9.2 from the textbook. This is a BJT amplifier, common emitter amplifier, and the problem is almost identical to what we did for the FET amplifier. Here again, we have three capacitors, CC1, CC2, and CE, which is bypassing the source, current source. We have to find those. So select the appropriate values for CC1, CC2, CE for the common emitter amplifier, and you're given all these resistances again: R signal, RB, RC, RL, GM also for this device, and you're given one more thing, which is R pi, which is the small signal model resistance, right? Actually, this should be small R pi, Rn. Sorry, it should be RB in parallel with R signal. I'll correct that later. Okay, so you have a little more data that is required if you're given a BJT, because it has beta and stuff like that in the formulas. But the formulas are, first of all, you find the REs, the Rs seen by each capacitor. Okay, so the RC1 is this, RC2 is this, and RE is this. In the previous example, here the R's are not called out separately. I just showed them as part of the frequency formula. The same thing exists here too. We've got this formula, this formula, this formula for omega p1, omega p2, and omega p3, which then help you get to the CC1, CE, and CC2, right? So the method of solving the problem is the same thing, but somehow when it comes to BJTs, the idea of first working on the resistances to go with each of the C's is an important exercise. Again, here also the low cutoff frequency, the minus 3 dB frequency, is still 100 Hertz, same as what we saw previously. And find also CC1, CC2, CE. Okay, so if you look at the solution, which is in your textbook, so first the R's are found, then each of the formulas for finding omega p1, omega p2, omega p3. But here, instead of taking 100 Hertz as the minus 3 dB frequency, and then assuming the other two should be so much lower, right? 10 Hertz like we saw for the FET amplifier, MOSFET amplifier. Here, the approach is slightly different. So what he advises us to do in the textbook is that select the CE such that 1 by CE RE, and RE is this whole thing. So 1 by CE RE is 80% of the frequency, the FL, which is the minus 3 dB frequency. So this 80% business is somewhat new. It's different from how we do it for the FET amplifier. For the BJT amplifier, the approach is slightly different. So you can see how he does the 80% calculation, right? So the goal frequency is 2 pi into 100, right? Which is about 670 radians per second. So of that he multiplies by 0.8, which is 80%. And that is the goal frequency to be achieved by CE. So 1 by CE then becomes 80% of that 2 pi 100, and using that he comes up with the value of CE as about 28 microfarads. Then he calculates, then he says, okay, so 80% of the frequency is taken care of. The remaining two capacitors will give us 10% of the frequency each. So then he multiplies 2 pi times 100 by 0.1 to get CC1, and again another 0.1 to get CC2. So using this method, he comes up with CC1, CC2, and CE. And you'll notice again that CE is much higher, hence maybe a more expensive capacitor than CC1 and CC2. So with this combination of these three capacitors, you will satisfy the rule that the lower cutoff frequency, the minus 3 dB frequency, should be 100 Hertz for this particular given NPN transistor. Okay. So I hope this method makes sense. Please practice this problem if necessary. I think for your exam purposes, I may be allowed to include one of the shorter questions. So maybe I'll have one 4 points question on frequency response, because I know you guys are studying this on your own, not in class, etc., etc. And I discussed it with the co-faculty, and they said we can have a simple question on the frequency response. So it won't be a full 20 points question, but it'll definitely be one of the shorter 4 points question. So you can expect one such question to come from all this material that we are covering here. Okay, so that was example 2. Now I have a few problems from the back. I think I've got 1, 2, 3, 4. So I've got 4 problems to cover from the back to cover the same material. So let's look at each one of them. So this shouldn't take too long. So hold on. Yeah, here is my handwritten problems solved on this chapter. So I call this file frequency response class problems part A. Okay. All right. So let's look at 9.2 first. For some reason I do 9.2 first and then 9.1. They're simple problems. You're going to find that there's not too much mental effort to do this, I hope. So again, we've got the CS amplifier. RD is given, RL is given, RD and RL. RO is very large, so anyway we were not considering RO at all in our analysis, which is the output resistance, the inherent output resistance in the device. So what's the question here? Find the value of CC2 specified to one significant digit to ensure that the associated break frequency is at or below 10 Hz. So we are only interested in this CC2. So only one formula needs to be used here. So I guess you can call it a very baby exercise. So let's see how to solve it. So is it 10 kilohertz? Just 10 hertz. Sorry. Okay. So FP3, yeah, FP3, because FP3 is related to CC2, right? Yeah. Find CC2. Using this formula, omega P3 is 1 by CC2 into RD plus RL. That means omega P3, which is 2 pi f P3, is 2 pi into 10, which is 63, right? So omega P3 is 63. So if you take CC2 in this formula, this side, it becomes 1 by omega into RD plus RL. So if you solve that, you get a value of 0.8 microfarads for this particular problem. Simple problem. All right, it's too simple. Let's move on to the next problem, which is problem 9.1. So here, the amplifier in the figure is biased to operate at a given GM. Here we have an extra resistance, right? So what you see in this emitter source circuit is not the current source that we were previously dealing with, but it's just an emitter. So there's a source emitter here. Of course, it's bypassed because the source emitter is only useful for biasing, and we don't want it to play any role in the small signal business or the small signal amplification. Okay, so note the presence of RS. Now, again neglect RO, determine the value of RD that results in a mid-band gain of minus 20 by 20. Determine the value of CS that results in a pole frequency of 100 Hz. So this CS should give us a pole frequency. Remember this term pole frequency, which is kind of new. Now we know all these are poles, right? Because they are in the bottom denominator of the transfer function. Poles versus zeros. So that's where this term pole frequency has come. So part B then is finding a value for CS with a goal of having a minus 3 dB frequency of 100 Hz. Then give an approximate value of the 3 dB frequency FL. Okay, well actually part B we are only finding F2, right? It's not exactly FL, but it's close. Then part 3 we actually find the real FL. Okay, so make sure you see that slight distinction. Okay, so part A has nothing to do with capacitances because we are only finding the mid-band gain. In the mid-band region, we always assume the capacitances are short circuits anyway, right? So part A is more like studying amplifier theory from the previous chapters, right? Part B and C have to do more with frequency response. All right. So what's the formula for A? Part A, that means the mid-band gain. Now this formula you recognize from, the amplifier chapters we've studied already. So mid-band gain That means from signal to output, including the load resistance if any, or the drain resistance, Rg if any, or signal if it's there. So this is your total formula, which simplifies to, in this case, minus GMRD, right? Because we don't have information on Rg, no R signal is given, RL doesn't exist, so it's the simplest form, which is minus GMRD. So I'm showing you both. In case you have a problem with more resistances, then you use this. If nothing is given, just use this. Then omega p, of course, you can find. This is 1 by RC, and GM is 1 by R for 2 milliamps per volt. So from there you can find omega p2. Again, if a source resistance is given, then I told you that the formula modifies slightly. So it becomes GM plus 1 by RS by CS. So in this case, because RS is given, we'll use this formula. Okay? Alright, so with all that background, let's see how to solve 9.1. So here's the formula, here's the simplified formula for mid-band gain. Now we know that we have been asked to reach a goal of minus 20. From there we have to find RD, so RD comes out to be 10K. Simple, right? Part B is worrying about the capacitance value, right? And the goal is Fp equals 100 Hertz. Actually, it's omega p2, I should say Fp2. So omega p2 is 2 pi f, which is 630. So hence Cs, if you take Cs to this side and bring everything down, you come up with 3.53 microfarads for Cs. In this case, we are just saying that FL can be approximated to Fp, which is 100 Hertz. Okay? Because all he's asking is an approximate value. He's not asking for a precise value. And an approximate value of FL, if no other information is given, is always, Fp2 or omega p2. So slightly different twist on the material, but again, not too complicated a problem, right? Okay. This third problem on CS amplifiers, frequency response, may be slightly more complicated. So let's see what it says. So the amplifier shown is a CS amplifier with a constant current source I. Now there is R signal here, there is RG, RL, everything is given, right? And GM is given. Again, three parts: find AM, the mid-band gain, design the coupling and bypass capacitors to locate the three low frequency poles at 100 Hz, 10 Hz and 1 Hz. Now we are given more specific data to work with. So this frequency has to be 100, the next has to be 10, next has to be 1. Use a minimum total capacitance with the capacitor specified only to one single digit. We'll see what that means. Finally, what value of FL results? Okay, so let's see how to do this. So all the data is given, many resistors. Now AM uses the longer formula and we come up with 16 volts per volt magnitude for the mid-band gain. The highest frequency, 100 frequency pole is Fp2. So 100 equals Fp2 equals Gm by 2 pi Cs. So either you can multiply the 2 pi to the frequency and work with radians, or you can work with hertz and bring the 2 pi below. So that's what I've done here. So Cs is the given Gm by 2 pi F. So that comes out to be 4.8 microfarads, which you can approximate to 5, because he wants us to approximate it to the nearest available real capacitor. Similarly, Fp3 is 10 Hertz. So for that, your Cc2 can be calculated using this formula, and you come up with 1 microfarad. And Fp1, which is 1 Hertz, you come up with a value of 0.1 microfarad. So you can see as the frequency lowers, the capacitance value also lowers. Here the capacitance is high, and I don't know what I said previously, but obviously for higher cutoff frequency, low cutoff frequency, you need higher value of capacitor, so it's more costly, right? Okay, so with these three values of C, now we have taken 100 nanofarads is 0.1 micro. Here we had Cc2, actually the value came out to be 0.53, but we bumped it up to 1, which is the closest available capacitor. So with the approximated or with the selected values of capacitor, we are running the numbers again for Fp1, Fp2, Fp3, and we are slightly off, right? This we want it to be 100, now we have achieved 95.5, and the other two we want it to be 10 and 1, so those are 5.3 and 0.64. Nevertheless, the rule is still satisfied that Fp2 is much greater than Fp1 and Fp3. Fp2 is 95, right? 95 is much higher than those. So you can assume that the FL, the actual minus 3 dB frequency, is Fp2, which is 95.5 as derived here. I hope this is clear. We calculated, then we chose something close to the calculated, then we recalculated and arrived at the final answer. Okay, all right. After this, I've got, let's see, I think I only picked one problem from BJTs. So it's a bit of a more advanced problem, but I'm not giving you as much exercise with BJTs as we did with FETs. So we only have one problem to look at for BJT. So this is an exercise from the textbook. So the answers are available. Let's look at the problem. So we have a, sorry, this should be our signal. So we have a CE amplifier with a bypass capacitor CE. I guess the capacitor is also called CE, and the configuration of the amplifier is CE. I should say common emitter. So this is a common emitter amplifier with a capacitor CE to bypass the current source. And we have the CC1 and CTC2. So this is pretty straightforward. A common emitter amplifier, we are given the CC values in this case as 1 microfarad, and we are asked to find what FL will be the result. So it's a bit of an opposite question, right? So far we were given a goal of an FL, that means the minus 3 dB frequency, and we were asked to find the capacitances. Here we are given the capacitances and asked to find the corresponding minus 3 dB frequency FL. Another thing that you'll notice is all three capacitances have a common value, 1 microfarad. So that's a bit unusual because normally we find that the CE, this capacitance, is much higher than CC1 or CC2. But anyway, that's the problem given. And so based on this information, we have to solve. The answers are also here, so we'll come back and look at it. But let's see what we did to solve it. Oh, sorry. Hold on. 914. Where is 914? Okay. I do have. Sorry, this is not 914. That's a mistake. It's exercise 9.2. Okay, sorry about that. Yeah, GM is 40, our pi is 2.5. Okay, so let's see how to solve this exercise. So first of all, beta is found as 100. Beta wasn't given, so but we are given GMR pi, so if you multiply the two, you get beta. Another thing that's important for these formulas is RE, the input resistance, the intrinsic input resistance, which is 1 by GM is 25 ohm. So we have the three formulas for FP1, FP2, FP3. I mean, you can first find this resistances R1, R2 and RE, or you can just directly write these formulas. So I've written the formulas, and you can calculate FP1 as 21.4 Hertz, FP2 is 2.19 kilohertz, FP3 is 12.24 Hertz. So the value of this FP2 is much higher than these two frequencies, right? So if that is the case, then you can just take that FP2 to be your minus 3 dB frequency, FPL, or in case of BJTs, we have this other formula where you add the 3 and you get somewhat of a more precise value for the frequency. So there's 2.19 or 2.24, they're slightly different from each other, not too different, but that is what he's telling us here. Since FP2 is much greater than FP1 and FP3, FL can just be FP2. This is approximately equal to. There you go. So with that, we can see what the answer is. So either answer is acceptable, a quick approximation is 2.21, or you can add the 3. In this case, it's not very different, 2.24 kilohertz. Okay, so that's the answer to this exercise. Okay, that's it. That's all the time we have for part A. In my next two recordings, first I'll do the theory of this material, 9.2 and 9.3, and then we'll have a problems examples recording also of 9.2, 9.3 with that, we'll finish with frequency response, and I guess that's also the end of the material for your course this semester. All right, see you later.